Hello everyone! In this video I'll be talking about concepts from Chapter 2 of Chemical Applications of Group Theory by Cotton, 3rd edition. Chapter 2 revolves around the definition of a group. Here are the questions to this chapter, and these are the questions that we are going to tackle in this video. The weak aspect of this chapter is that it overestimates the power of Cayley tables, the kind of algorithm that Cotton uses to find various groups, which is by varying the number of identity elements on a diagonal, will break for G8. As a supplementary material, I used Visual Group Theory, a YouTube course by a mathematician, and I recommend it to anybody who is interested in more theoretical aspects of chemistry. The link is below. Lastly, I assume you watched my previous videos on group theory. If not, I'll try to summarize the most crucial points. If you want to skip it, please look at the timestamp below the video. So let's start with briefly revising the definition of a group. To have a group, you have to have a set of elements, A, B, C, etc., and you need to have some operation that allows you to combine these elements together, like addition, multiplication, function composition, if elements happen to be functions, etc. Therefore, the operation is called binary. You need two elements to accomplish something. This is in contrast with non-binary operations, like taking a square root or taking an absolute value, where you need only one element. Also, please notice that in jargon, the binary operation is referred to as multiplication, and the outcome as product, even in cases where the binary operation is not actually multiplication. So anyhow, let's assume we have some set of elements and a binary operation. On top of that, 4 rules have to be satisfied. First is closure. For any AB in the set, the product AB must be also an element of the set. The second is identity. One element in a group must commute with all other elements and leave them unchanged. Chemists usually use the letter E as the identity element. Next is inversion. Every element must have an inverse, which is also an element of the group. If element R is an inverse of an element S, then please notice that S and R commute, that is, RS equals SR equals E, where E is the identity. However, do not expect that to be true for any pair of elements in a group. That is, if R is not an inverse of S, do not expect RS be equal to SR. For majority of groups, the commutative law does not hold. Having said that, there are groups where all elements commute, and these groups are called abelian. The last requirement is associativity. In other words, brackets can be placed anywhere but are required nowhere. If this brief summary is not enough, please watch my video on the definition of group, where I provide some specific examples. Next, let's revise Cayley table. So Cayley table is like a multiplication table where each entry is a product of two elements. This particular table is for C3D group. The elements of the groups are symmetry operations, and the binary operation is just performing one symmetry operation after the other. You can fill in the table by just performing the symmetry operations on some molecule which has C3D symmetry, for instance ammonia molecule. So let's look for instance at this entry. If we do sigma V1 first, and after that sigma V2, the overall result of the two operations is that of C32. Please notice that we have to adopt some conventions. We multiply the element from the column first, followed by the element from the row, and we write it like this. So the multiplication is from left to right. The alternative, opposite conventions are also frequently used, so always check what is the convention in the book or video that you are learning from. Next thing I want to mention is the rearrangement theorem. It states that each row and column in the Cayley table lists each of the group elements only once. Let's analyze the proof. Suppose that in a row A, the element G appears in the column B and C, that is, BA equals G equals CA. Let's write multiply by A inverse, and that gives us B equals to C. This is not a contradiction. We just shown that B and C are in fact the same element. In other words, the B column and the C column refers to the same column. Also, you might wish to notice that when we write multiplied, we use the property A times A inverse is identity. This is referred to as the cancellation law. In this particular case, the right cancellation law, because we multiplied from the right side. An analogous proof can be done for columns. Next, let's talk about inverses. Every element has unique inverse because if we assumed otherwise, let's say if G has two inverses K and H, we would just arrive at the answer that K is equal to H. Knowing that, could you please tell me if this set of 8 elements, E to H, can be a group and why? To clarify the diagram, 3 elements are their own inverses, including the identity element, and 5 elements are not their own inverses, so they must be inverses to one another. Please pause the video and I will discuss the answer in a few seconds. The answer is that it cannot be a group. Let's say we have an element X, what inverses can it have? Well, it can be an inverse to itself, that is x equals E, or it can be an inverse to another element, let's say Z. But please notice that if X is an inverse to Z, then Z is an inverse to X. In other words, we always have to leave pairs that are inverses to each other. That's why the table cannot represent a group. We see 5 elements that apparently are inverses to each other that cannot be, as the number has to be even. It is very important, as basically the entire chapter is based on making Cayley tables by varying the number of elements that are their own inverses. For instance, for G8, we can speculate that there could be potentially 2, 4, 6, or 8 elements that are their own inverses, but not 3 or 5. The last proof is that the identity element is unique, but I will leave it for you to analyze it. Next, let's look at some important types of groups. We will start with cyclic groups. Let's look at this shape. It is made of 4 tiers, and I colored each tier differently so that we know what is the position of the shape. We can rotate it by 90 degrees, and the shape will preserve its footprint. That is, it will look the same. We would not be able to tell the difference if I did not mark the tiers with different colors. We can rotate the shape second, third, and fourth time, and this time the shape returns to the initial configuration. We can say that the shape has rotational symmetry. In fact, cyclic groups describe objects that have only rotational symmetry. Let's focus on the diagram once again. It shows the states of the shape that we rotated. But there are many similar shapes that would behave exactly the same way, so it would be better to just focus on the actions that we are performing. In fact, the actions are the elements of the cyclic group. And if you watched my video on symmetry elements and symmetry operations, you know that chemists use groups which elements are symmetry operations, like rotation, reflection, etc. So this is not new to us. So if we call rotation by 90 degrees R, then this is the diagram with actions. We start from the initial configuration 1, we perform rotation R, then we perform rotation R again, so overall, to get from the initial configuration to the present configuration, we need to do R squared. Doing R again takes us to R cubed, and doing it again takes us to R to the power of 4, which is also the initial configuration, that is 1. So R squared, R cubed, and 1, or R to the power of 4 if you prefer, are the elements of C4 group, that is cyclic group with 4 elements. In general, Cn group has 1 R squared all the way up to R to the power n-1 elements. So C6 will have 6 elements, C5 will have 5 elements. Of course, the value of R in these two groups is different. In the case of C6, it will be 60 degrees. In the case of C5, it will be 72 degrees. To sum up, one example of a group of order n, Gn, will always be a cyclic group Cn. Order of a group Gn is just simply a number of elements in that group n. To hit point home, if someone asks you, give me an example of, for instance, G14, that is group with 14 elements, you can say one example could be a cyclic group with elements 1 R squared all the way up to R to the power 13. Please notice that chemists would label the elements in a cyclic group a bit differently. Mathematicians often give the identity element symbol 1, as anything multiplied by 1 gives the same thing back. Chemists like to think of the identity element as E. I will be using both notations in this video. The last thing on the slide is that any cyclic group is abelian. That simply comes from the fact that r to the power of k times r to the power of m commutes. Now let's think about a Cayley table for C4, so r is 90 degrees. To tackle this, we first need to realize that if we do r 5 times, that is r to the power of 5, it gets us back to r. Similarly, r to the power of 16 reduces to 1, or r to the power of 4 if you like, and r to the power of 27 reduces to r cubed. Now we can construct a table. Please notice that because cyclic groups are abelian, that is, the order in which we do operations does not matter, the table is symmetrical along the diagonal. Now let's do a thought experiment, and let's say we want to move in r² increments. Let's call r² a capital R. Please notice that r² increments does not allow to reach r or r cubed, only r² and 1, as it is necessary to start at 1. Now we can create a Cayley table with elements big R and 1, and with little effort we can see that these two elements fulfill the requirement of a group. There is an identity element, every element has an inverse, closure is fulfilled, and although we cannot see it directly from the Cayley table, associativity is fulfilled too. You can check it if you want to. Such a group inside of other group is called a subgroup. Let's do a similar thought experiment. Let's rename r cubed as capital R, and let's go around the circle in r cubed increments, once, twice, 3 times, 4 times. Now we ended up where we started, and this time we were able to reach all elements in C4 group. That's probably a good moment to mention so-called generators. A generator in a group is an element that you can use to generate other elements in a group. It is customary to use minimum number of generators. Cyclic groups only require one generator, and for C4 group, we can see that either R or R cubed would do the job, although R is more convenient. Soon we will meet groups that have to have at least 2 generators, but for now, let's finish off the cyclic groups. Let's do another example, C6. Let's think how many subgroups it has. Well, r² generates r², r to the power of 4, and 1. And we'll see that this set of elements make up C3 group. R cubed element generates r cubed and 1, and it corresponds to C2 group. And r to the power of 4 generates exactly the same set of elements as r², and so we will ignore it. And lastly, r to the power of 5 generates all elements of C6 group, so both r and r to the power of 5 can be a valid generator for C6 group. In general, for a cyclic group Cn, any element Rx, which has index x relatively prime to n, will generate all elements of Cn. The last important thing is to realize that a cyclic group can only have cyclic subgroups. This is kind of obvious from the diagrams that we have just analyzed. A link to a formal proof will be in the description. Now we are ready to do this example. Show that for any cyclic group x, x², all the way up to xh, there must be one subgroup corresponding to each integral divisor of the order h. Please pause the video and give it a go. The answer is obvious, and I will leave it for you to analyze it. It is just a written form of what we just shown graphically. Let's move on to second very important category of groups, dihedral groups. Dihedral groups describe regular polygons, regular triangle D3, square D4, pentagon D5, etc. Dihedral groups have 2 types of symmetry, rotations and reflections. So let's focus on group D3 that describes a regular triangle. Here is a diagram with states of a triangle, and here is a corresponding diagram with actions. Let's look at the diagram with states of a triangle first. Let's start at the gray triangle. The red arrow represents generator R, rotation. We rotate, rotate again, and that takes us to the starting configuration. Notice that it is exactly what we would have for C3 group, and indeed, C3 is a subgroup of D3. It is also very visible on the diagram with actions. The diagram for D3 is just the diagram for C3 plus some extra bits. So let's concentrate on these extra bits. There is a blue line. The blue line corresponds to a horizontal reflection, which is a second type of generator for D3. Please notice the plane needed to achieve horizontal reflection is vertical. Here you see the beauty of generators. A chemist would say that a regular triangle has 3 rotations and 3 reflections. A mathematician would say that a regular triangle needs 2 generators. Let's show it. Let's start at the shaded triangle, let's do rotation, and then horizontal reflection, and the overall effect is that of another reflection. Super cool. Only with a single reflection, in that case I chose an arbitrary horizontal reflection, and a rotation r, we were able to create the effect of all the other reflections. Please notice that the dihedral group Dn has r rotations, E is counted as r to the power of n, and n reflections. In other words, Dn has 2n elements. That means that for any group with even number of elements greater than 2, you can construct a dihedral group. If someone tells you to come up with 2 different groups for G4, now you have the knowledge to suspect that one will be cyclic group C4 and the other dihedral group D2. Another thing I would like to point out is that the generator, horizontal reflection, is presented on the diagram as a line, not as an arrow. It's because it is its own inverse, so the direction does not matter. Let's look at the starting configuration. Let's do reflection, we are here, then let's do reflection again, and we are back where we started. With rotation it's different. Let's start at the initial configuration again, let's do rotation r, and then let's do r again, and it does not take us to the initial configuration, but to r squared. So with rotations, it's a one-way road, so to speak, except 180 degrees rotation, of course. The dihedral groups are non-abelian. Let's show it. If we start at the initial configuration and we do rotation, then reflection, we end up here. But if we start at the initial configuration and do reflection, then rotation, we end up here, at a different position than before. An exception is D2. D2 can be perceived as a group describing a rectangle. Here there is a diagram with states of the rectangle and the diagram with actions. For D2, the rotation is by 180 degrees, and it commutes with the reflection, and therefore the group is abelian. So let's explore now all possible groups for G2 and G3. There is only one way we can fill in the Cayley table for G2. You may think about it as C2 cyclic group. Let's move on to G3. We know that any element multiplied by the identity gives the same element back. So that leaves us 4 unknown entries. The way Cotton approaches it is that he tries different number of identity elements on the diagonal. We already said that the number of elements that are inverses to each other must be even. That means for C3, either all 3 elements are their own inverses or just one, only E. As it turns out, the first case is impossible. We see that if E is here, then here we have to have B. But we cannot, as here is B as well. That will not be a group. The second option works. AA is B, and so we have no repetitions in the table. Please notice that this group is cyclic. We have A, AA is B, and AB is AAA, which is equal to the identity element. Let's move on to group G4. We can either have 2 or 4 identity elements on the diagonal. The one with 2 E elements on the diagonal is actually the cyclic group C4, and I'm sure you can construct it by yourself. The second is easy as well. Let's look at this entry, for instance. It cannot be A because there is A above, and it cannot be B, so it has to be C. That's why here we have to have A and so on. There is also another way to arrange the elements in a table. It's easy to spot by looking at this table. Please pause the video and give it a go. So maybe you spot that these 4 entries can be rotated by 90 degrees. Now we come to the weaknesses of the Cayley table. This table is in fact this table, with the following mapping. E and C is mapped to E and C respectively, so nothing changes there. But A is mapped to B, and B is mapped to A. The tricky thing is that after such a swap, the appropriate columns swap as well, so that the order of rows and columns EABC is preserved. If you have problems seeing the swapping, let me help you. First look at this entry. We have A, but the mapping tells us to change it to B, and so we see B. Then let's look at these 2 entries. We see BE, but the order of these 2 rows must swap. So now E is at the top and at the bottom is not B but A because B goes to A, and the same happens here. And then we have to deal with the square. Please follow the dot. When we swap these two rows, the dot goes here, and when we swap these two columns, the dot ends up here. So the overall effect is that the square rotates by 180 degrees and A changes to B. So these two groups are called isomorphic, as there is one-to-one correspondence between the elements in these groups. In fact, they are not counted as distinct groups. So we say that for G4, there are only two distinct groups, the cyclic C4 and the dihedral D2. Next, let's explore all possible groups for G6. This is actually one of the exercises at the end of Cotton's chapter. The groups could have potentially 2, 4, or 6 elements that are their own inverse. The exercise tells you that the last option is impossible, so let's deal with it last. Let's leave these two and let's see which of these two is the cyclic group. We can see that C6 group has only two identity elements on the diagonal, for E and C elements. I'm sure you can finish off this table by yourself, so let's move on to the other table. That's where it can get slightly more challenging for you. To make any sort of progress now, you need to make assumptions about 4 relationships in this table. Just pull it out of the hat, as we have no means of distinguishing between the elements. Depending on what relationships you choose, the table will look different, but such groups should be isomorphic to one another. However, I kind of like to have a little bit more insight in what I do, so let's think about it. We have 4 elements that are their own inverses, that could potentially correspond to their identity element and 3 reflections, so that is a hint that this group can be perceived as D3. Also recall that C3 is a subgroup of D3, and therefore we can fill in this part assuming that E and for instance A and B make up C3 group. Now at least we have something that makes more sense. Now let's look at this part. Here we cannot have A or B or E, so it must be either C, D or F. So let's look at these 2 entries. It can be either D or F, so let's assume that CA equals D and CB equals F. And now we can fill in the rest. You just need to use the known relationships. For instance, let's write multiply by B, then we have CAB equals DB, but we know that AB equals E, and so C equals DB. So we must have D here, and so on. I actually will walk you through this step by step in the solution for exercise 2.5, which is in the coming videos. I will post a link below when I finish rendering it. Now let's finish off this exercise. Let's show that it is impossible to put 6 E elements on a diagonal and obtain a group. We already have relationships like AA equals E, etc., but we need to have some extra relationship to move forward. So let's pick BA equals C. Then we can multiply it by B from the left and by A from the right, and that gets us 2 other relationships. Now let's look at these 2 entries. We can have here D or F, and of course we cannot have DA equals D because that would imply that A is the identity element. So let's take DA equal F, and that allows us to get A equals DF and A equals FD. Next, let's look here. We see that BD must be F, because all the other letters are already present in the column B, except D and F. This leads us to the following table, and now let's focus on this entry. After analyzing the row and column this entry is in, we can see there is nothing we can put there without repeating elements, so this cannot be a group. Next, I would like to introduce you to direct product of groups. For now, we can think of direct product as a way of making bigger groups out of smaller groups. Let's construct direct product C2 cross C3. This group has 6 elements. Each element is a 2-tuple of the form NM. N can be any element from C2, and M can be any element from C3. So you can see there is 6 possibilities. This is a Cayley table for this group. How do you fill in such a table? Well, the group operations are done component-wise. The first entry obeys the rules for C2 group, and the second entry obeys the rules for C3 group. So let's look at 1b. What is 1b times 1b? Please remember that the first term refers to C2, and 1 in C2 is just r squared, that is full rotation. What is the effect of full rotation followed by full rotation? Well, we come back to the starting configuration, that is 1. And then let's look at the second entry. What is b followed by b in C3? Well, it's b squared. As in C3, we can associate b with rotation by 120 degrees. 120 degrees done twice gets us overall to 240 degrees, that is b2. Now I want to show you that this group C2 cross C3 is in fact isomorphic to C6. Why do I want to show it? After all, isomorphic groups are not regarded as distinct groups, so why do I go through the trouble? Well, C6 is isomorphic to C2 cross C3, but C8 is not isomorphic to C4 cross C2, and I want us to have some practice. So to show that C2 cross C3 is isomorphic with C6, we need to find the order of all the elements in C2 cross C3. Order of an element is the power to which we need to raise the element so that we get to the identity element. In other words, how many times we need to repeat the element to get to E. Let's find the order of the element 1b, since we already started calculations with this element. So 1b times 1b is 1b squared. So let's see what 1b squared times 1b is. 1 times 1 is still 1, for the same reason as before. However, b squared times b is now 1, because b to the power of 3 in C3 group is equal to the identity. So we get 1, 1, the identity element. So the order of the element 1b is 3. The rest I will leave for you to analyze. If you have a question, please ask in the comments. The point is that one element has order 2, 2 elements order 3, and 2 elements order 6. I will skip the identity element because no matter how many times we repeat E, we will always get E back. So assigning an order to the identity is kind of customary. Now please realize that in C6 group there is also one element of order 2, 2 elements of order 3, and 2 with order 6. And then there is the identity element. After closer look, you can see that if we swap the label 1b with ab, the orders of the elements between C6 and C2 cross C3 will match. So there is one-to-one correspondence between elements of these two groups. So the group C2 cross C3 is indeed isomorphic to C6. And now we can even see that colors in these two tables match. To sum up, we now have some idea what direct product of group is. For more information, please look at the links below. Direct product will be useful when dealing with group G8. Now we need to approach groups like G5 or G7. To do that, we need to get familiar with some theorem. The order of any subgroup G of a group of order H must be a divisor of H. That is, H over G equals K, where K is an integer. The proof is in Cotton, but it is very dry because it lacks visuals. So I would strongly recommend you a video by a math major on YouTube. The link is below. It is very clear and well presented, and I am not going to reinvent the wheel. The theorem is actually called Lagrange's theorem, but of course, don't expect chemistry book to mention that. Whether you watch the video or not, I just want to stress that the Lagrange's theorem says that it is possible for a group Gn to have subgroup of order that divides n, and that it is not possible to have subgroup of order that does not divide n. However, the Lagrange's theorem does not say that Gn have to have subgroup of order that divides G. An example can be a group A4 that has 12 elements but no subgroup of order 6. Another thing I want to mention that was really absent from the video with the proof is the consequence of the Lagrange's theorem. The consequence is that the order of any element A of a group divides the order of that group, since the order of A is equal to the order of the cyclic subgroup generated by A. For instance, the orders of elements of group C6 that we already looked at were 6, 3, and 2, that is, the divisors of 6. So what? Well, let's look at group G5. We can always construct a cyclic group C5. In that group, every element has order 5. We cannot have another group G5 because the orders of the elements would have to be different, but that cannot be since all elements have to have order 5, since 5 is a prime number. Next question is of a type, please repeat what I have just said, and I will leave for you to read the answer if you like. The next question is also very easy. The cyclic group C5 has one E on a diagonal, and your job is to show that Cayley table with 3 and 5 identity elements on a diagonal is not possible. The next question is more interesting because it contains an error. It asks, why can we not have a group in which a squared equals b squared is not equal e? Well, we can. Let's for instance look at some cyclic groups of even order. The answer is this. I think the author forgot to specify that the question refers to G3. In that case, it would make sense. For G3, there is only one way to fill in the table, such that AA equals B and BB equals A, but if AA equals BB, then indeed A equals B. The last question in this video is about G8 groups. Invent as many different groups of order 8 as you can. Please pause the video and give it a go. Based on what we have said, I'm sure you would suggest some of these groups. The elements of the group C2 cross C2 cross C2 are 3 tuples of the form MMM, where M can be 1 or R. There is another group called quaternion group, but it is not even included in the solution, as the relationships between elements are a bit more complex, and it would be difficult to come up with it just by playing with the Cayley table. When we analyze the number of identity elements for each of these groups, we can see that the kind of algorithm which Cotton uses to find different groups, that is by varying the number of identity elements on diagonal, breaks for G8, as there are 2 distinct groups with equal number of identity elements. Having said that, I do not think that the author was writing this chapter with the aim of introducing any mathematical rigor. A mathematician would first establish relationships between generators and then fill in the table. I will attach a link to such a document in the description. Cayley table is a rather primitive tool. If you want to explore group theory in more detail, as I said, I recommend a course of visual group theory. The link is in the description. So that's all I have for you. I hope it helps. Thank you for watching. Bye!